Hello everyone, I'm Jiaqi Gao, a fourth-year PhD student at Harvard University. Today I'm going to show you what does incident routing look like in data center and how to improve the diagnosis process through domain-customized incident routing. This is a joint work with the University of Pennsylvania, Microsoft Research, and Microsoft. Availability and maintaining service level objectives are the biggest challenges facing cloud operators today. Operators are working hard day and night to keep the complicated system up and running. However, incidents can and do happen. Here is a table that collects the public incidents of the past 6 months in Google Cloud and Azure. We can see that Google Cloud reports 69 incidents and Azure reports 21 incidents. It takes both clouds hours to resolve the incidents. Note that these are just public incidents and there are way more incidents under the cover. Now let's see the life cycle of an incident. Firstly, when the monitoring systems deployed in the data center detects the abnormal behavior or the customer is experiencing issues, an incident is created. The next step is finding the failing component. In a data center, different components are managed by different teams. For example, the network devices are managed by physical networking teams. The virtual disks are managed by the storage team. So finding the failing component equals to finding which team is responsible for the incident. This process is usually done by asking each team whether the problem belongs to its components. If so, then the team takes over the incident and apply the corresponding troubleshooting procedures. If not, then we need to find the next team until one team claims the incident. Just like when we debug a buggy software, rather than fixing the bug itself, we often spend most of the time finding where the bug exists. From our measurement, finding the right team is time wasting. Here is a CDF curve of the normalized investigation time when one or multiple teams investigate the incident. We can see that in the median, misrouted incidents takes 10 times longer to resolve compared with incidents that were sent directly to the responsible team. But how can this happen? Let me first give you an example. Here is an example incident from Azure. One day, a customer complains to the support team that she cannot write to the storage. Since it seems to be a storage issue, the support team operator sends the incident to the storage team. After a quick check, the storage team finds their system is good and suspects the network is slow and sends the incident to the networking team. But the networking team sees no congested link. Now we seem to reach a dead end, and the storage team sends the incident back to the support team to collect more information from the customer. After further digging, the support team finds that the connections to the storage failed to initialize and thus suspects the software load balancer is not functioning. The incident then bounces between the SLB team and the networking team twice because neither team thinks their system is faulty. Finally, after some inspection, the SLB team concludes the reason is that the customer opens too many connections and exhausts the software NAT pool, and the behavior is expected. In this example, it takes so many rounds and involves so many teams to figure out the problem. We want to ask why? Why multiple teams get involved in one incident? To answer this question, we studied 200 misrouted incidents in Azure in depth. To our knowledge, this is the first case study focusing on the reasons behind cloud incident routing problems. We found that there are three common reasons. First, engineers from different teams bring a wide range of domain knowledge to determine culpability. The involvement of multiple teams is due to a lack of domain knowledge in a specific area. For example, the storage team engineers may not know whether the network is functioning or not. To make things worse, team-level dependencies are deep, subtle, and hard to reason about. In our example, to use the storage, the packet has to traverse the network, software load balancer, to reach the storage. So when the customer complains the storage is failing, any team is a legitimate suspect. As a result, misrouting happens. Secondly, when no teams in the cloud are responsible, more teams get involved. Because operators in the data center usually lack the visibility into other ISPs and customer systems, which may be experiencing ongoing DDoS attacks or bugs or misconfigurations. It is harder to collect information outside the cloud and thus hard to debug remotely. In this case, it is sometimes faster to rule out teams within the cloud first rather than wait or blame others. As a result, this ends up involving more teams. In an example incident, it is the customer that is misusing the storage system, but all the related teams had to investigate and prove that they are guilty-free. Thirdly, concurrent incidents are hard to isolate. Sometimes the same issue may trigger multiple incidents, one for the component at fault and one for each service that depends on the component. But before the root cause is discovered, all the affected teams have to investigate the problem in parallel. On the other hand, if two incidents are concurrent but not related, operators may mistakenly link the two, which causes misrouting as well. So, how to reduce misrouting? Previously, people tried to solve this problem with two approaches. First, they built application-specific diagnose systems, such as NetPro, which detects networking problems, DeepView, which takes care of virtual disks, and Sherlock, which localizes bugs in the applications while inferring dependencies. These systems are built specifically for each application and can diagnose whether it is working properly or not. But because there are too many applications in the data center, we cannot build one diagnose system for each application. Another line of work tries to route incidents based on the incident text description, such as a global incident routing system running in Azure, which is built on top of the NSDI 13's work, NetSieve. But because it fails to consider the domain knowledge in each team, which is one of the main reasons for misrouting, the accuracy is not high. So here, let's revisit our incident routing problem. We want to build an incident routing system that when an incident happens, the system can summarize the engineer's domain knowledge and other resources, such as the monitoring data, and send the incident to the correct team. The first guess would be building a well-defined algorithm that is able to summarize all of these inputs, which is hard and really challenging. Then another approach is machine learning. We can let the machine learning algorithm learn the pattern. There are many ways to build such a machine learning system. The simple solution would be to build a huge machine learning algorithm that solves the problem at once. But we quickly found that it is really hard to build such a single monolithic incident routing system with high accuracy. There are 4 problems. The first problem is that the curse of dimensionality. Because the global routing system should consider everything, this large amount of information can easily result in a huge feature vector, but because we don't have enough examples to train it. The second problem is uneven instrumentation. A subset of teams will always have gaps in monitoring, either because the team has introduced new components and analytics have not caught up, or simply the monitoring is just hard. The third problem is the input is constantly changing. We may constantly experience stale components and monitors. The fourth problem is limited visibility. Because we are sitting at a global position, it is difficult to understand the appropriate feature sets from each and every team. So here we present Scout, a team-specialized gatekeeper. Instead of sitting at a global position, the per team-based Scout simply answers the question, is my team responsible for the incident? So when an incident is created, the Scout can run local checks and intercept or reject the incident based on the result. The design has 3 advantages. Firstly, each team only needs to maintain 1 Scout, so this solution is realistic and applicable. Actually, according to our findings, not all teams need to build their own Scout. Only teams that are inordinately affected by misroutings should build a Scout. Secondly, per team-based Scout can easily leverage the team's domain knowledge, such as what are the team's responsible components, what are the monitoring systems deployed in the data center. Thirdly, each team can evolve its own Scout independently without affecting other team Scouts. Here shows our proposed high-level structure of a Scout. Given the incident, the Scout uses the domain knowledge of the engineers to collect information such as the monitoring data. Next, the Scout uses a computation engine to analyze these domain-specific information and returns a classification result. In this paper, we show how to build a Scout for physical networking team, one of the teams that is mostly affected by misroutings. The physical networking team is in charge of each and every switch and router in the data center. The engineers in the finance team build 11 different monitoring systems, such as Ping Mesh, Everflow, and NetBouncer, that collects a massive amount of monitoring data. We've also done some investigations to quantify how severe is FiNet affected. We found that 58% of the incidents investigated by FiNet went through multiple teams, and in total, 97.6 engineering hours per day are wasted on unnecessary investigations. So we think it is really necessary to build a Scout for the FiNet team. The first challenge of building the Scout is how to process this huge amount of data. We can see previously that millions of the switches in Azure are monitored by 11 different monitoring systems. And it is impossible to analyze all of them together at once. So we need to shrink our search space. And our insight is the instance itself can guide the investigation. The instance description usually can tell us the candidates of the affected components, such as the affected servers, switches, and clusters. For example, this made-up instance description describes a server experiences issue connecting to another storage cluster. Because data center components are named after predefined naming conventions, we can encode them through regular expressions and extract the potential devices out. For example, in this incident, we can extract one server and one cluster. After this step, we can find related devices monitoring data, such as CPU usage, link loss rate, and ping latency. Through this method, we can shrink our scope and collect a reasonable amount of monitoring data. Then the next challenge is how to create a feature vector out of the monitoring data. The machine learning model requires fixed length feature vector, but different incidents may have different number of components. How to merge them into one feature vector? Remember, we have 11 different monitoring systems. Some of them are event-based, such as the reboot event. Some of them are time series, such as the ping latency data. How to summarize them together? Here, we propose a two-tier solution. We first build a fixed length feature vector for each component extracted. Next, we merge all of the components' feature vectors together into a new fixed length feature vector. In the first step, for the event-based monitoring data, we sum the number of events during the incident period. For the time series monitoring data, we normalize the data and compute a series of statistics, such as different percentiles, average of the data. When merging the feature vector from different components, again, we compute statistics such as percentiles and averages, etc. So through this algorithm, we can build a fixed length feature vector for each incident. Okay, the third challenge is which computation engine do we use? There are many algorithms available, such as unsupervised learning and supervised learning, and statistic-based algorithms. Which algorithm do we use? So the algorithm we choose is supervised machine learning. The benefit of the supervised machine learning algorithm is it learns based on historical incidents and related monitoring data, and thus it has a really high accuracy. But because this algorithm is trained on top of historical incidents, it has low accuracy on new or rare incidents. Besides, we also want to make the machine learning model explainable and provide more insights to the engineer rather than just say yes or no. So we choose the random forest algorithm. The random forest algorithm classifies input feature vector by constructing a multitude of decision trees and summarize the classification result of each decision tree. We can go through how each decision tree processes the input feature vector to provide more insights. So how can we overcome the drawback that random forest algorithm has low accuracy on new or rare incidents? Since any learning algorithm won't work well, we need to look for statistical analysis solutions. Here, we use the change point detection algorithm. In a nutshell, the change point detection algorithm is able to detect the change points in a time series of monitoring data, and we believe these change points usually is an indicator of abnormal behaviors, thus might be the cause of an incident. The change point detection algorithm has benefit that it is really easy to compute because it does not need a training phase. It has higher accuracy on new or rare incidents compared with the random forest algorithm, but unsurprisingly, it has lower accuracy on old incidents. So how to merge these two algorithms together? How to choose which model to use? As we said previously, if the incident is recurring or common, then the random forest algorithm has high accuracy. So again, this can be formalized as a training algorithm. We can let the incident itself tell us whether it is a new or old incident. The model selector uses meta-learning to identify new incidents. If the selector thinks it is a recurring incident, it will send the incident to the random forest model. Otherwise, it will call the change point detection algorithm. Okay, till now I've introduced all of the components in our Scout, and here is the framework. The input of a Scout is the incident description. The description is a collection of texts describing the incident and related components. Next, the Scout extracts related components from the incident text via a configuration file. The configuration file contains the regular expressions that describes the naming convention of the related components, and this is the only information required from the operator. Given the related components, the Scout pulls related monitoring data out and sends it to the computation engines for feature construction. On the top line, the model selector chooses which computation engine to execute by judging whether the incident is new or not. At last, the selected computation engine returns the classification result, and the system can either reject or accept the incident accordingly. Now let's see how this Scout performs. We collected 9 months of incidents in Azure and randomly split the incidents into the training and testing set. For labeling, we said one incident is a positive incident if it is resolved by finite at last. For the baseline, we compare the incident routing system without Scout's involvement. The current instant routing system includes the engineer's runbooks, past experiences, and the NLP-based routing system we introduced previously. Here is the table showing the overall performance of the system. We show the overall performance in 3 metrics: precision, recall, and F1 score. The baseline can achieve around 90% of the precision and recall, and here is the result of a Scout. Compared with the baseline, the Scout can gain 10.3% on the precision and 5.8% on the recall. This shows that our Scout can perform better than the current system and classify the incidents at really high accuracy. But what does this 10% improvement mean? How can this 10% improve the incident routing system? To show the benefit of a Scout, we introduce another metric called gain. The gain is the amount of time we could save when the Scout makes the correct prediction while the baseline is wrong. Depending on whether the incident is resolved by finite, there are 2 types of gains. The gain in calculates how much time we could save by accepting one incident and send it directly to finite. This describes the amount of time we could save for other teams. Here is a CDF graph that shows the gain in. The x-axis shows the percentage of investigation time we could save. The blue curve shows the gain in of a Scout. We can see that for 40% of the positive incidents, we can save more than 20% of the investigation time. Here is another curve showing the best possible gain we could get, which is a gain in when Scout has 100% accuracy. We can see that the blue curve is close to the orange curve. So the Scout can significantly reduce the investigation time and close to the best possible result. For the incident that were not resolved by finite, we still have the gain called gain out. The gain out shows how much time we could save by rejecting the incident. This shows the amount of time we could save for finite team. Again, here is the graph showing the gain out. We can see that the 2 curves are still close to each other, which means the Scout performs close to the optimum. Apparently, the Scout could make mistakes, and we can measure the time wasted by the overhead. Please check our paper for the result. In a nutshell, the overhead is close to the minimum. Due to the time limitation, there are a number of things we did not talk about. The first thing is the design and evaluation of a Scout master that combines multiple Scouts and summarizes their results together. We also did not talk about a series of extended evaluations, such as how the Scout performs over time, the sensitivity analysis, and the result of other design choices. At last, we also wrote down the lessons we've learned from the deployment. Please check our paper for more detail. In conclusion, we showed that instant misrouting is the main challenge for maintaining service-level objectives in the cloud. And we proposed the Scout, a distributed team-specialized gatekeeper that can reduce the total incident investigation time. That is all of my presentation. Thank you for your listening.